Hey, what's going on, guys? Welcome back to another stream here. I hope all of you guys are doing well. We're back with another one. We're back again. We're back. We're focused. I did take a break there for a while, but now it's 7:50, and we're gonna work up until like around 10 o'clock. I will have to take a break in the middle, but hopefully it won't take that long. Yeah, sorry about that. And yeah. We're back. I don't know why this thing keeps on starting. I'm gonna just get rid of it. I'll just remove it. Alright. So what we said what we were gonna do was we're gonna finish the chemistry course after revising a lot of these chapters. So the ones that I said I was going to do, I was going to do VSE PRT. I was going to do acids and bases, oxidation reduction. There's some tricky ones there as well. You get me? A test for anions, lab safety signs. That's what we're going to focus on. Then if you have extra time, we're going to do atomic theory 8, 9, 10. And we'll do atomic theory 1 through 5 quickly. And then yeah, that should be good to go. Okay, so let me just sharpen up my pencil and let's get straight into this. So it says state or predict the shape. Okay. Account for the difference in the shape between NH3 and CH4. Mention no shape. 3 bonding pairs, 0 lone pairs. Different shapes. Lone pairs have, yeah. Talk about the bond. Okay, lone pairs have a greater repelling effect than bonding pairs. So the number of lone pairs in NH3 push it together. Yeah, okay. Okay. I think I kind of understand it, so I'm just going to do some past papers now on this topic, hopefully. And let me just drink some water. Let's get refreshed. Let's get back into it. So I want to work hard. I want to do well in my exams, of course, but sometimes it feels like it's running away from you. Yani, what you need to do. You're not getting enough done. But that's all in your head. Like, you're capable of so much. Use that to your advantage. You're blessed with so much. Use that to your advantage. Yeah. You have the ability to gain education. Like, what more of a blessing do you want in your life? Because, like, I'm telling you. So it says, Liebigser 2019. State and account for the shape of an OF2 molecule. So if you look at OF2 is, first of all, how many atoms? 3 atoms. So 3 atoms we said could be V-shaped, or it could be linear. Now, we need the periodic table, which is beautiful. We have that here. Now, I have 1 oxygen. So let's say I'm going to put oxygen here. Oh, now oxygen we know has 6 electrons in its outermost shell, and we know that. So how many does fluorine have? Fluorine has 7 electrons in its outermost shell. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Fluorine, 7. So this oxygen is going to have to share 1 here. It's going to share 1 here. But we said the oxygen has 6 electrons in the outermost shell. So 1, 2, 3, 4. So 2 bonding pairs, 2 lone pairs. So really it's going to be V-shaped. V-shaped. right? It says state an account for the shape of the OF2 molecule. Sorry, let me just double check something. So let's state an account. Account for the difference in the shape, state or predict the shape. So we know it has two bonding pairs, two lone pairs, V-shaped. Now it says 103 degrees, 180 degrees. Select giving your reasons which of these angles is the most preferable value for a bond angle in oxygen difluoride. 103 degrees, as there are two bonding pairs, two lone pairs, therefore what shape do we have? We have a V-shaped molecule. Now state and account for the shape of tetrachloromethane. So tetrachloromethane is going to look like this. So first of all, we know it's going to be 4 bonding pairs, 0 lone pairs, and 4 bonding pairs, 0 lone pairs, and therefore it's a tetrahedral shape, right? The lone pair, I guess you could say state and account. Lone pairs have a greater repelling effect than bonding pairs, therefore pushing predict the shape of boron trifluoride. So it's either going to be trigonal planar or it's going to be pyramidal. Boron has 3, right? Okay, so straight away we know it's going to be 3 bonding pairs, 0 lone pairs, so it has to be trigonal planar. Now it says to predict the shape of ASH3 molecule. ASH3, so AS has how many? AS has 5. H3. So 3 bonding pairs. Well, you write it like this. Of course you wouldn't do BP bonding pairs. 1 lone pair. Therefore it is pyramidal. So really it would be something like, they're not asking for all this, but I'm just going to show you what they mean by that. Like something like that, right? Now it says account for the difference in shapes. So they don't want the shape. We know that the shapes are different. So boron trifor. So that's trigonal planar. So that means there's 3 bonding. So boron trifluoride has 3 bonding pairs, 0 lone pairs. Ammonia has 5 and 3 has 3 bonding pairs and 1 lone pair. The lone pairs have greater repelling effect than bonding pairs, therefore pushing the bonding pairs closer together. I think that's what it is. Let me just double check that. Sorry. I'm so sorry. So the number of one, so the no of lone pairs in energy. Lone pairs have a greater repelling effect than bonding pairs, so the number of lone pairs in NH3 push it together. Okay, let me just double check something, yeah? Let me just go on Gemini. Count for a difference in shape between boron and trifluoride. Of course, 3 bonding pairs, 0 lone pairs. Yeah. Strong repulsive force. The lone pair aggressively pushes the NH bonds downwards. Yeah. Lone pairs push bonding pairs downwards closer to each other in energy compared to BF2. Okay. It says ammonia and silane are small molecules, each of which has 4 electron pairs in the valence shell of the central atom. Account for the difference in the bond angle between the 2 molecules. I mean, account pretty easy. I mean, that's 3 bonding pairs, 1 lone pair. And then silane is just 4 bonding pairs, 0 lone pairs. So therefore different bonding angles. Give the shape and the corresponding bond angle for a molecule of QX4. Straight away tetrahedral bond angle is 109 degrees. What are 2 possible shapes for molecules general formula QX2? QX2 means 3 atoms. So linear or V-shaped. Account for the difference in the bond angle 104.5 degrees to methane. So water has 2 bonding pairs, 2 lone pairs. Methane has 4 bonding pairs, 0 lone pairs. So in water, the lone pairs have a greater repelling effect than the bonding pairs, so therefore it's going to push those hydrogen atoms, those bonding pairs between the hydrogen and the oxygen closer together to form a V shape. Then how would you excite the hydrogen sulfide molecule in linear and non-linear shape? And it's, yeah, okay, easy enough, okay. Wait, the one that was hydronium, yeah, H3O plus is like, let's say I have oxygen, and let's say I have like here, bang, 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 like that. So oxygen has, we said 6 electrons in its outermost shell. So 1 here, 1 here, 1 here. I'm actually enjoying studying, bro. I never really enjoyed studying, bro. I can't lie. But now it's actually fun. So 1, 2, 3. Actually, you know what I'll do? It actually would be something like that. Because those lone pairs have a greater repelling effect than these bonding pairs. So something like that. Oxygen, bang, 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 bang. So it's 3 bonding pairs. And then it's like, oh yeah, don't forget the plus. It's 1 lone pair, so it's pyramidal molecule. Pyramidal molecules, my friends, have 107 degrees bond angle. Yeah, my bro. And then of course you have dative covalent bonding as well, where only one atom supplies the electrons for a covalent bond. I think that's in this VSCPRT, right? Date. Is there dative covalent bonding? Okay, that's fair. Okay. I think we're going to do test for anions now. Test for anions. And anions. Test for anions. Bang. Sulfate, sulfide, hydrogen, hydrogen, carbon. So some of you lot may be like, oh, this guy is just like, he's under pressure now, yeah? Yeah, Key, I'm a bit under pressure, but... Like, I've studied everything, like, I need to study. Like, right now it's just revising over, just refreshing the memory. Like, so now we have sulfate and sulfide. So I believe, first of all, reagent is going to be barium chloride, right? So sulfate is going to be sodium sulfate. So Na2 SO4 plus BaCl2 barium. It's group 2, yeah. Barium Cl2, sorry, is going to give me yeah, so it's going to be BaSO4 plus NaCl, but it's 2 NaCl. And then if I do the same, I have Na2. So this is a white precipitate, I'm pretty sure. Then if I have Na2SO3 plus BaCl2, I'm going to get NaCl plus BaSO3, like that, yeah? So this barium sulfate is also a white precipitate. Now, to tell difference, remember we had that using a halogen to oxidize the sulfate to a sulfate to a sulfide. Using halogen to oxidize sulfate to sulfide. So, okay, if that's correct, then sulfate precipitate will not disappear, but sulfide will. Wait, I don't know. Wait, let's check. Let's check. That's why we're here. So, sulfide ion is present, but if it doesn't disappear, sulfate. Yeah, so that was the halogen, using a halogen. So either chlorine water, bromine water, or iodine water, with chlorine water being the strongest oxidizing agent. Then distinguish the white precipitate disappears, the sulfur dioxide gas is given off, the sulfate ion is present. So it's dilute hydrochloric acid in it as well, yeah? Alright, so distinguish the white precipitate disappears, sulfur dioxide gas is given off if the sulfite ion is present. Okay, so sulfide ion, so sulfur, sulfate, no reaction. Sulfite, sulfite is the one. So sulfate has no fate, where sulfite took a shot. No, I'm joking. Alright, so sulfates. So I dilute hydrochloric acid. It's gonna give me BaCl2 plus SO2 plus H2O. So that's 3 oxygens, 3 oxygens, 2 hydrogens, 2 hydrogens, 2 chlorines, 2 chlorines, 1 room. Yeah? Yeah. Sulfur dioxide gas is given off. Alright, so barium chloride, white precipitates form. Sulfate, no reaction. Sulfite, there's going to be a reaction because we use dilute hydrochloric acid. Now we have test for ions, and we have a hydrogen carbonate and the carbonate ion. So first of all, we're going to add any dilute acid, e.g. dilute hydrogen chloride. For example, hypothetics. Alright, so add any dilute acid. For example, let's say I take dilute hydrochloric acid, right? So I have NaHCO3 plus HCl. Sorry, it's gonna give me NaCl plus H2O plus CO2. It's actually correct, yeah. And then here I have Na2CO3 plus HCl. I'll balance them, right? NaCl plus H2O. I think it's magnesium sulfate that we add, right? Yeah, two chlorines, two hydrogens, one carbon, two, three. Yeah. Here we have one sodium, one chlorine, one chlorine. Yeah, okay. One chlorine, three oxygens, Oh yeah, we balanced them already. Nice, lovely. Now test for carbon dioxide gas. So you know it gets quite gassy out here. You get me? So we need to test for the carbon dioxide gases. Anyways, alright. So how do we test for a carbon dioxide gas? Is we're going to bubble the carbon dioxide water through lime water, which is calcium carbonate, and we're going to get Ca, so calcium hydroxide. No, lime. Oh, lime water is calcium hydroxide. Calcium carbonate. Yeah, sorry. CO2 plus calcium hydroxide, which is lime water, is going to give me CaCO3 plus H2O. So calcium carbonate, just a scum. So white precipitate. Yeah, or scum. or scum. Alright, so this is lime water. So this is one carbon, two oxygens, four oxygens, a calcium. There's nothing to balance. Yeah, nice. So test for so we're going to bubble the carbon dioxide through lime water, and it will get a white precipitate forming of calcium carbonate and H2O to a colorless solution. So bubble the carbon dioxide through a colorless solution of lime water. The lime water turns milky white. Then we are going to add magnesium sulfate. Plus SO2 plus H2O. Oh, sorry. No, you just swap the metals. Plus Na2SO4. And then Na2CO3 plus MgSO4 is going to give me MgCO3 plus NaSO4. So this is a white precipitate. So if it's a carbonate, a white precipitate will form. If it's a hydrogen carbonate, there'll be no white precipitate upon the addition of magnesium sulfate solution. Now boil clear and colorless solution. Boil clear and colorless solution. If you boil the clear and colorless of hydrogen carbonate, then we know that hydrogen carbons decompose on heating. That's why temporary hardness can be removed by boiling. Ah, that makes sense. So we looked at sulfate and sulfide, barium chloride, right? We had barium chloride solution to both white precipitate forms. Then we add dilute hydrochloric acid. In the sulfate no reaction sulfite, we get the white precipitate disappears and carbon dioxide gas is given off. No, sulfur dioxide gas is given off. Sulfur dioxide. So I think it's barium chloride plus SO2 plus H2O. Then hydrogen carbonate and carbonate. We're going to react it with any dilute acid, so hydrogen chloride. So hydrochloric acid. Sorry, hydrochloric acid. Hydrochloric acid. We react that together. So we're going to get NaCl plus CO2 plus H2O. Then we have to test for carbon dioxide gas. So CO2, bubble it through lime water, colorless and clear solution of lime water, CaOH2 is gonna give us calcium hydroxide, is gonna give us calcium carbonate and H2O. And a color solution of lime water, we're going to bubble it through a color solution of lime water, and we should get a white precipitate carbonate of calcium carbonate. Now, how do we tell the difference between a hydrogen carbonate and a carbonate? Is we're going to add magnesium sulfate to both. Now, in the case of hydrogen carbonate, a white precipitate is not going to be formed. In the case of carbonate, if a white precipitate forms, carbonate is present. Then if I boil the hydrogen carbonate, the clear and colorless hydrogen carbonate solution, I should get a precipitate of magnesium carbonate as hydrogen carbonate is decomposed upon heating. Then we have a few more ions. So we have nitrate ion left. So nitrate ion, this is the brown rings tests. These actually come in clutch, bro. These get you some nice marks, bro. So we want, so what do we want? Reagents. We have freshly made iron 2 sulfate solution and concentrated H2SO4, sulfuric acid. Freshly made iron 2 sulfate solution and concentrated H2SO4. So add sodium nitrate solution to a test tube with water. Add fresh FeSO4 solution, which is greenish in color. Add concentrated H2SO4 solution. Add concentrated H2SO4 solution carefully down the inside of the test tube. You must use concentrated for this test to work. The sulfuric acid falls to the bottom as it is more dense. If a brown ring forms at the junction, a nitrate ion is present in aqueous solution. So we're going to add a few centimeters cubed of silver. We're going to add sodium nitrate to a test tube containing water. Now we're going to add a few centimeter cubed of concentrated sulfuric acid. It must slowly down the inside of the test tube. So we're going to tilt the test tube and add concentrated sulfuric acid slowly down the carefully down the inside of the test tube. Must be concentrated for the reaction to work. Now we're going to add a few centimeters cubed of iron 2 sulfate solution. So add fresh FeSO4, add concentrated solution. If the sulfuric acid falls to the bottom as more dense, and if a brown ring forms at the junction, then the nitrate ion is present. So add silver nitrate to a test tube containing water, right? So you add silver nitrate to a test tube containing water. Then what do we do? What do we do? Is we add freshly made iron 2 sulfate solution to the test tube, which is greenish in color. And then we're going to add concentrated sulfuric acid. We're going to tilt our test tube to the side. We're going to tilt our test tube slightly and carefully add concentrated sulfuric acid down the inside of the test tube. Now the reason why it has to be concentrated for this reaction to work. Now the sulfuric acid is going to settle at the bottom as it is more dense, and if a brown ring forms at the junction, then the nitrate ion is present. Okay, so I was a bit slow, I can't lie. Diagrams, do we need a diagram? Oh shoot, we might need a diagram, bro. Can't lie, cause I'm not into that diagram stuff, bro. I won't lie. I mean, what is there to the diagram? It's like this, right? Right. Yup. AgNO3. Then I pour in, what did I say? Freshly made FeSO4. Then I'm gonna tilt it. Yeah. I'm gonna slowly down the inside. This is concentrated sulfuric acid. Then, you know, so if a brown ring forms at the junction, then a nitrate ion is present because you have iron sulfate. That means the diagrams are not like, so chloride, if you're using silver nitrate reagents, so silver nitrate solution, add silver nitrate solution to an aqueous solution, add silver nitrate solution to aqueous solution of sodium chloride. Oh yeah, because we need chloride ions. And add few drops of concentrated nitric acid solution, which is HNO3. Immediate light precipitate form. So if I have sodium chloride plus silver nitrate, I have silver it's an ionic reaction. To confirm the white precipitate is chloride. So HNO3. To confirm the white precipitate is a chloride ion. We add dilute ammonia solution. White precipitate dissolves as silver chloride is soluble in dilute ammonia. And then we have phosphate ion. I can hear your mercy every rising. Phosphate ion, right? So we're going to add, reagents is ammonium molybdate solution. So add ammonium molybdate solution to Okay, so we're going to go through all the anions tests. Sulfate, sulfide, add barium chloride solution. When we add barium chloride solution, so we have NaSO4, Na2SO4. I believe we just swapped the metals. So white precipitate is formed. So barium sulfide, white precipitates. Right, now we're going to react these precipitates. So now we're going to add dilute hydrochloric acid into both test tubes. If a sulfate ion is present, the white precipitate remains because there's no reaction takes place. But if a sulfide is present, the white precipitate disappears and sulfur dioxide gas is given off. So H2O plus SO2 plus barium chloride is our product. Okay, then we had hydrogen carbonate and carbonate. So sodium hydrogen carbonate, we add we add any dilute acid to both of these test tubes containing our carbon and hydrogen carbon. So any dilute acid. So we're going to use dilute hydrochloric acid because that's the one that we're most familiar with. So then we should get NaCl plus H2O plus CO2 for both of the products. Then we have to test for the presence of carbon dioxide. So we're going to react the carbon dioxide with lime water, which is calcium hydroxide, to give us calcium carbonate and hydrogen gas. So we're going to bubble it through this colorless solution of lime water. Then we're going to add magnesium sulfate to both. So essentially what happens is I believe you just swap the metals. And hydrogen carbonate, there's no white precipitate. Carbonate ion, there's a white precipitate forms. But if we then heat the colorless and clear solution of containing the hydrogen carbonate, and we boil it, therefore we form the magnesium magnesium. So we form that white precipitate, and H2O and CO2 are given off as well. So because we know that hydrogen carbon is decomposed upon heating. Then we had nitrate ions. So we add silver nitrate solution to a test tube containing water. Then we're going to add freshly made iron to sulfate solution, which is greenish in color. We're going to tilt the test tube slightly, and we're going to carefully add concentrated sulfuric acid down the inside of the test tube. Now we're going to, then sulfuric acid is more dense, so it settles at the bottom. And if a brown ring forms at the junction, nitrate ions are present. At chloride ions, we had our reagents with silver nitrate solution and a few drops of concentrated HNO3. So then it's just ionic reaction, so it happens instantly. Swap the metals, bang, bang, done. But if we want to determine is it a chloride ion, we're going to dissolve the silver chloride in dilute ammonia. If it's in dilute ammonia solution, the white precipitate disappears. Therefore, we had silver chloride present. Yeah. Then we have the phosphate ions. We're going to be using ammonium molybdate solution with we're going to add that to a test tube containing phosphate ions, and we're going to very carefully carefully add five drops of concentrated HNO3. And we're going to heat gently, so no heat, no reaction, so that's the condition. And if a yellow precipitate of ammonium phosphomolybdate will form if phosphate ions are present. Okay, I think we're good on that front. Not too worried, cause rest of this can get done like in like one day. Put one shift in, and you can get everything done. Yeah. We could probably get these two chapters revised, all of this revised again, all of this revised again, all of this revised. But I think I leave that for another day because I don't want to spend too much time on it because I have done it before. I did want to do some physics though, I won't lie. I wanted to do a lot of past papers. You know what? I think I genuinely need to focus on my languages. Yeah? We'll do physics tomorrow, yeah? But right now, I need to focus on getting just Irish just done and dusted. Getting her llama bug done and dusted. I won't lie, I might just put in a shift now and get her llama bug and Oshin done. Yeah? And I might do a bit of Macbeth. Alright.